Okay, I'm using a pretty new software, so hopefully this will work well. What I'm going to do is fly through a review of UCM, which is chapter 9 in your book. And at the end, I'm going to do UCM with gravitation, some of which should be review, some of it might be a little bit new. We'll see, but you should be in great shape for tonight's homework. Okay, so you remember UCM is all about going in circles, and the idea is that UCM stands for Uniform Circular Motion. And it's with a constant speed, and direction is always changing because you're going in circles. Okay. And I'm really going to fly through this. So just hold on tight, and you might want to pull out your notes from chapter 9. We did this at the end of mod 2, the second mod of physics. Okay, and the deal is that we can't use A equals VF minus VI over T. We can't use kinematics in that way because the speed is constant, so the V's are constant. But what we do use is we use A sub C, which is centripetal acceleration. Remember, that's the good word. We're allowed to use that one. And that's equal to V squared over R, where R is the radius, because of course we're talking about circles. And some other equations you need are that speed, and this is speed, not velocity, right, equals 2 pi r over t, where t is that same t that we've been talking about, the period. Okay? It's the time for, in this case, one circle. You guys know it as one cycle, that's seconds. Okay, r is the radius. I can't imagine you don't know that, but just there you have it. Okay, cool. And F is still equal to 1 over T, just like it was when we did springs. You see how nicely this fits together. Okay, blah, blah, blah. And the idea is that you have centripetal force, and it is always pointing into the center of the circle. Okay, and so is A sub C, and the V is always tangent to the circle. All right, and so F sub C in general is mv squared over r because it's m times a, mass times acceleration. That's Newton's second law. We already talked about A, so there you have it. Okay, that's a whole bunch of review equations all at once. And when we did this, we did a lot slower, but we also talked about what kind of forces would cause things to go in a circle. We talked about tension, right? We talked about a ball on a string going in a circle. We talked about normal force. We talked about the washing machine and the sock, or, some clothing, or the salad spinner with some lettuce. All those things are examples of centripetal forces. The one I want to do today is gravitation. Okay, so we're going to look at gravitation as your F sub C because we're going to be looking at orbits. And so obviously things go in orbit because of gravity. Just a quick reminder about Newton's law of gravitation. I'm pretty sure you've seen this. And this just says for any two things that have mass, the force, they have a gravitational force between them. It's an attractive force, and it's equal to capital G times m1 times m2 over, and we've used d squared and r squared. I'm going to use r squared. Okay, so m1 and m2, those are the masses of the two objects that we're talking about, and that's in kilograms. R is just the center-to-center distance between them. And the reason that's a big deal is because we're talking about planets and suns. And so whether you're talking about their center or their surface, that really makes a difference. So center-to-center distance, that's in meters. You'll know that that's squared. That's super, super important. And then G is a constant. It's known as the gravitational constant. It is 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared. And if you put that all together, you will get the gravitational force between the two objects, and it is in newtons. And each object feels the same force. Really important. It's just feeling it in an opposite direction. Right? So if you've got object 1 and object 2, they are both attracted to each other. They are both going to feel the exact same force. I'm pretty sure I told you this, but just in case, I remember solving for the force and thinking you had to divide by 2, that they must share it. No, this is, you calculate it, G, M1, M2 over R squared. That is the force that you calculate. That is the force that each one feels. Now, why don't we see this in real life? Because G, this big G, that's a really small number, right? You really only see this with really, really big objects like planets and suns and stuff like that. So I want to be focusing on that. And what I want to do is I want to compare what happens when you have something like a planet going around a sun. And we talk about the acceleration due to gravity. And let me do one derivation, and then I want to talk about the acceleration due to gravity and how it's all connected. Okay? So first, let's do planet around a sun. And it could be around anything, right? It could be moon around a planet, I don't know, an asteroid around a star, anything. But let's just do a planet around a sun. And the idea is that you've got the sun and you've got the planet. That's a planet. Okay, and we're talking about the center to center distance, r. And the idea is that it feels a gravitational force, and it is that gravitational force that causes it to go in a circle. I'm not going to draw the whole circle. You get the point. So remember the steps that I want you to do is I want you to say, all right, Fc is Fg. That's the force that's causing the circular motion. Fc equals mv squared over r. And these are all the things, all the variables associated with the thing that's going in the circle. So in this case, that would be the planet. Okay? This belongs to the thing going in a circle. Okay, so we would say this is equal to G, M planet, M sun over R squared. Again, that R is that center to center distance. This is equal to M planet, V of the planet, if you like, squared over R. And they're equal to each other. So G, MP, MS over R squared equals MPV squared over R. And you do some cleanup work. One of the R's goes away. The mass of the planet goes away. It actually doesn't matter. And if you wanted to look at the speed of the planet, it's going to be equal to the square root of G times the mass of the sun times how far away it is from it. Having said this, this is not an equation that you start with. Where do you start? You always, 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 always start right up here. I want to see that every time. Okay, so does the AP. We all want to see that. This is just a little monkey equation. You know, congratulations, you can do some algebra. That's great. Always a good thing. Not what we're doing here. So if you're going to use this, you need to derive it. Okay. The other thing you should remember is that we can talk about the speed of the planet as far as its period. Right? That's still a thing. So this is something that you can use to help you find the period of a planet. And when we're in class, we'll talk about some cool things like geosynchronous orbits. Okay, so that's gravity in circles. I think that's review, or if it's not, it should be pretty close to review. Here's another idea that might not be a review. And this is looking at acceleration due to gravity. And honestly, I can't remember who I've taught this to, if anyone, so I'm just going to start as if we've never done it. So if you are someone and you are on Earth, let's say, okay, you're on the surface of the Earth, we know that if you're just standing there, the force on you is the force of gravity. And we've always said, okay, well, we're just going to use the force due to gravity is your mass, that's you, little m, times 9.8, right? Or m times g. I want to show you where that comes from. We can actually look at Newton's law of gravitation and say, okay, well, the reason that you have this, and this is your weight, yeah, is you take g, your little mass, the mass of the Earth, over the radius of the Earth squared. Why the radius of the Earth? Because that is your, this was poorly planned on my part, that purple line, that is the center to center distance between your center and the Earth's center. Do we need to worry about you and your belly button or anything like that? No, because the radius of the Earth is huge. Okay, but hey, check it out. If I set these two things equal to each other, I could actually solve for G. I'm just going to call this G right now. So big G, mass of you, mass of Earth over the radius of the Earth squared equals the mass of you times little g. Well, once again, interestingly, your mass cancels out. Okay, and if you look, these are all constants. The G I just gave you, the mass of the Earth, you don't need to know this, but it's going to be pretty cool for these purposes. Let's see, the mass of the Earth is 5.98 times 10 to the 24th kilograms. The radius of the Earth is 6.38 times 10 to the 6th meters. If you plug that in, okay, pay attention, square your RE, hey, you should get 9.8. That's where that comes from. That's pretty cool. But what if you weren't on Earth? What if you were like, I don't know, a certain distance above the Earth? Or what if you were on Mars? Well, you could go ahead and once again do this process to figure out what the acceleration due to gravity would be on those different places. Okay? So each time, the way I want you to start is by doing this, saying Fg equals big G, m whatever is the person, yeah? M of the planet or the moon or whatever, over that distance squared. And that person might be on the surface or might not. If you're not on the surface, then you've got to take the radius of whatever that is plus like the little height, right? That whole thing would be the radius. So I'm going to call this radius of the planet. That whole thing would be the radius that you would look at. This would be the whole R. All right, and you set that equal to m of the person times g, and again, this is going to be your acceleration due to gravity of wherever you are. All right, that was a super, super fast version of this. We'll do more in class. We're going to talk about what it means to be weightless. You might want to check out the OK Go video just for fun. We're going to talk about Kepler's laws. We're going to talk about the potential energy due to gravity. We got lots to talk about, but for right now, go do your homework. Okay, bye.